Welcome everyone. You are joining us for Managing Laser Degradation in Industrial Applications. This webinar is presented by MKS Ophir and hosted by Photonics Media. Today you're going to hear from John McCauley, a Senior Business Development Manager at Ophir, where he focuses on automotive and directed energy applications. In this session, he is going to share how the variabilities of laser degradation can be managed, what aspects should be analyzed, and what tools are available. You can ask questions or leave comments in the chat box at any time. If you have any technical issues during the event, please log out and back in to rejoin. You will be able to access a recording of this webinar online after the event, and you will receive a link to that recording in your email inbox. So with nothing further from me, I'd like to welcome John McCauley. Welcome.
Hi, Joanna. Thanks so much for allowing me the platform to speak today. It's always a pleasure to work with Photonics Media, and it's always good to talk about something that is very important to people who are using industrial lasers for material processing. And I appreciate you spending an hour of your time today with me as we cover this important topic. And it is indeed my hope that you can walk away with something that is useful to you in whatever role you are working with respect to industrial lasers. Ophir is part of MKS Instruments. We are part of the Motion Photonics and Optics group you see in the third column there. Ophir, we manufacture solutions for measuring laser performance. So that's what we're going to talk about today with respect to that particular product line. To kind of frame the conversation today, let's talk about advancements in laser technology just from a 30,000-foot view. So I'd say probably one of the greatest advancements in laser technology over the past few decades is the application of fiber optic cables and lasers. This has certainly revolutionized the way that the laser is maintained, the way that the laser is built, obviously, the way that the light is delivered to the process. We have more efficient laser sources, so better wall plug efficiency. We have more flexible, and I put that in quotes, kind of a pun there, I guess. But we have more ways of delivering the beam, better ways of delivering the beam, and obviously decreased maintenance that come from these fiber sources and fiber delivery systems. In addition to that, the adaptation of Industry 4.0 manufacturing environments is another really key advancement in manufacturing that has affected the way that lasers are looked at, the way that the lasers are operated. We have an ever-evolving approach to manufacturing. It seems to me that the way that parts, just in general, are manufactured with respect to Industry 4.0 and those practices are just overall they're better. And as a result of these practices, we want more data about our process so that we can continually improve, oftentimes during the process, improve upon those processes and just make parts better just in general. But that has really spawned a need for the input of data on the laser. So we've got laser engineers that are coming out of school that are really just very hungry for data about their process and more specifically to what we're talking about, data about how the laser is performing. But given these advancements in technology, we still have to face the fact that lasers and laser systems are still made up of physical matter. So the components delivering the light, the components shaping the light, the component that is allowing the light to interact with the process, they're all made up of physical components. These, because of the environments that these lasers work in, they will get dirty, they will degrade over time. Laser systems, and I'll talk about that in a slide coming up here, but laser systems just naturally will decrease in efficiency over time. Sometimes it's quick, In the past with some laser systems, as we'll talk about today, that is a relatively rapid degradation of laser components. But again, these laser systems are getting better and better designed to where these are less of a process or less of an adverse effects on the laser system. But that's not to say that it does not happen. We have to face facts and realize that, because these lasers are made up of physical matter, they will degrade, and understanding of that degradation is really key to the process. So as far as an agenda today, let's talk about the problem. The problem is the degradation of laser components and the effect that these degradations have on the designed laser performance. There are some key laser performance characteristics. So understanding what characteristics of your laser is suitable for measurement, how often those measurements need to be taken, and just in general, better understanding of how your laser beam is behaving. There are a lot of measurements that we'll talk about this morning, but if we could whittle it down to make it very simple for you, we'll talk about just a couple of laser measurements that characterize the performance of the laser with respect to the process. And then there are 3 case studies that I'd like to talk about: a marking application development application, sheet metal cutting, and then welding application development. I'd like to talk about those case studies and how these measurements really helped improve these 3 particular processes. And then at the end, we'll, as is customary, we'll open it up for a Q&A, probably the last 5 or 10 minutes. So the problem: laser components degradation and the effect on the design laser system. Professor Seth Lloyd at MIT, I've mentioned a couple of times this year. I don't know if he knows that I quote his quote, but I do like this quote that he put out, because it certainly is applicable to what we're talking about, and that is: matter will always seek a way to revert from order to disorder because of the transfer of energy. And as a result, a system's ability to do work decreases over time. That is a general definition of the second law of thermodynamics. Professor Seth Lloyd says nothing in life is certain except death, taxes, and the second law of thermodynamics. That certainly applies to what we're talking about today. Because of the transfer of energy, these laser components are going to naturally seek a way to come back to its natural state and degrade over time, which in turn will decrease the overall system's ability to efficiently process material. So there are a lot of reasons why a laser would not operate as designed, regardless of how the laser is applied. Sometimes there are faulty component manufacturing. Sometimes the components themselves are faulty. The way that the components are made, the way the components are integrated with each other. Improper maintenance is one that I see personally quite a bit, and that's usually where these problems will arise. But there are also environmental factors. If you're working with industrial lasers, chances are you're working in a relatively dirty environment. That environment has adverse effects on that laser system. Sometimes there are contaminated cooling water, contaminated purge gas, sometimes due to improper maintenance, sometimes due to component failure. But all these ideas can add to the decreased efficiency of the laser system. So as long as laser systems are susceptible to human error and physical limitations, the performance of the laser systems will change over time, and let's face it, usually not for the better. It's the second law of thermodynamics at work. Understanding that there are going to be laser changes in your laser performance, and measuring these changes is really the best way to manage these changes, is the argument that I'm going to make, and hopefully you can agree with me with the points that I make with you today. So talking about how laser components degrade the overall the system of the component, let's just look at a typical laser system. So you start off with a laser source. That laser light is generated through some kind of lasing medium. Usually today it's a fiber laser, in the past has been ND-YAG or CO2. And when we take a beam profile of that particular laser, you have something that's nice and beautiful and round, and the energy is distributed, and everything is great. And then you send it to some kind of delivery system, whether it be free space optics. Today there are process fibers. You marry the process fiber with the source fiber through some kind of coupler. Sometimes you'll have purge gas or apertures or shutters and things like that. And then this nice, beautiful round beam has the potential of changing somehow when it touches something else. When it passes through something else, it has the potential of changing. And then finally, the beam is delivered to some kind of processing head. So there's some kind of beam shaping optics, some kind of scan mirror, some way of controlling the beam, shaping the beam, focusing the beam. And then your beautiful, nice beam, once it has, it's passing through all these components, and it's coupled, and something is wrong, not sure what, it may eventually end up like this. So the point that I'm trying to make is that when laser light touches all these laser components, every time it touches something, it has the potential of changing. And understanding how these components will contribute to the change in the laser light is really key to understanding how the overall system is going to be affected with respect to the process. So as a bonus case study here, I wanted to talk about this particular laser system that I got involved with some years ago. The laser system here, you see it was a free space optic system. It was a 1 kilowatt system that was used for additive manufacturing research. It was an open cavity, so there were bellows, there were turn mirrors, there were optics, and as a result of it being in an additive manufacturing, using powder, for this direct metal deposition, it was a relatively dirty environment. So, you had all those factors going against it. So the laser beam is coming down to a focusing optic and going through. You see the measurement equipment. This product is called the Beam Watch. It measures focus shift, and then you see the laser power puck, which is collecting the laser light and providing a laser power output. This particular system had a very fast focus shift, and they didn't know the symptom that was exhibited was they would start off at the beginning of a join of a layer, and then by the end of the layer they were losing joining. So they were it's just a very inefficient system. We suspected some kind of focus shift, but we didn't really know for sure without measuring it. But they had a loss after just a few seconds. So the troubleshooting was started, analyzing the beam at the process, and then we worked backward in the laser source. So we checked the cover glass. That was the first, that's usually the culprit. But this particular lab was good at cleaning this cover glass and changing it when necessary. So we did not see any problems with this particular cover glass. And then we worked backwards. So we see this arrow here is approximately the location of this isolation optic that was on the system. We took it out and looked at it, and this optic was really dirty. So you can see a picture of the optic. You can see a whole lot of dirt, a whole lot of contamination on this particular optic. This was the culprit that was causing the focus shift, just this thermal effect from the light being absorbed into this contamination on this particular optic was causing this focus shift. We took this optic out. It took 10 minutes to clean it, and then as a result, there was no more focus shift. So that was a very interesting case study for us. Key laser performance characteristics. There are a ton of different characteristics that you can measure on your laser. Let's talk about what's important. So to maintain a high efficiency laser system in production, the operator must understand how the laser interacts with the material being processed, right? You must understand how that light is behaving, that it's focusing down to a point. You've got so much laser light focusing down to a point, some kind of shape, some kind of roundness, some kind of possible variability. the laser operator must understand what laser performance characteristics to analyze and when to analyze those characteristics, and also what causes these parameters to change over time is really very important for the laser operator to understand. There are, again, like I mentioned a second ago, there are a ton of different laser performance characteristics to measure. I think everybody here can appreciate that measuring laser power or energy at the work site is really a key indicator for how that laser is performing. So tracking that over time, I think most industrial lasers users understand that measuring this particular characteristic of the laser is really key to understanding its performance. There's the pulsed laser characteristics. So if it's a pulsed laser, understanding, and verifying pulse frequency, pulse shape, pulse width, those are all very important to understand. And then there's laser beam geometry. We go into the laser beam profiling part of the measurement. So is it a top hat? Is it a Gaussian profile like it's designed to be? Understanding the shape of the beam, the ellipticity, the roundness of the beam. And then the focus spot position. So if you are presenting the focus spot to your process, is that focus spot, is it where it's supposed to be, number one? And after the laser beam is on, if there is a thermal effect on the laser system, like we saw in that case study, is that focus shift drifting off of where it's supposed to? So understanding where the location of the focus spot is and if that location is changing over time is very important to understand. And then there's laser quality measurements like M², beam parameter product, divergence angle, Rayleigh length. These are all very important, typically in the system runoff or in the application development, definitely in the laser source manufacturing part of the laser life cycle is very important to understand these characteristics. But the bottom line is there are a ton of different measurement characteristic measurements that you can take, and it's not always that practical to stop what you're doing and take all these measurements. So if I can make it easy for you, I would love to do that for you. So let's narrow it down. Which laser characteristic is best helps me understand how a laser is performing, and that is power density. I think anybody who's working with industrial lasers using in the application is familiar with this particular term. It's known as a lot of different terms: energy density or fluence, irradiance, luminescence, depending on what kind of laser you're working with. But the general definition of power density is the amount of laser light produced per beam size. So it's how much laser light that you have with respect to the beam size that's being applied to the process. And it's expressed in this expression here, watts per centimeter squared, or a variation of this particular, but it's the amount of laser light in watts. It could be joules, it could be, kilowatts, it could be milliwatts, but per centimeter squared, per area, surface area of the beam being applied. In this case, it's watts per, centimeter squared. It could be inches squared, whatever else. So to illustrate how beam size affects power density, I want to use this just general illustration. We've got two lasers here. Both of them are fiber lasers, 1070 nanometer wavelength. Both of them operating at 100 watts. On laser number one, you've got a beam size of 5 millimeters. Very large beam, relatively large beam, okay? I'm using an extreme example here just to make the case, so bear with me. On the laser number two, you've got a 50 micron spot size, so you got a much smaller beam size that's being applied. Same laser power, same 100 watts, so how does that affect the power density? On laser number one, you've got a power density of 5.1 times 10 to the second watts per centimeter squared. Power density number two, you've got 5.1 times 10 to the sixth watts per centimeter squared. So basically the bottom line is, with a 100 times smaller beam, it'll yield a power density that's 10,000 times higher. That's why it's very important. Again, this is an extreme example, but it is very important to understand how the beam size applied to your process, any changes in that, is very key to understanding the process. Let's look at this a little bit deeper. You have the same 100-watt laser. Say that you've got it focused down to a 100 micron beam size. That's yielding a power density of 1.36 times 10 to the 6 kilowatts per centimeter squared. And say you have this lens that's improperly cooled. So it's improperly cooled. You're going to have some kind of thermal effect on this particular lens that's going to cause the beam size to get larger. It's going to cause this focus shift. So for the same 100-watt lens, 100-watt laser power, you now have a 250 micron beam size at the work site. Well, what changed? The power density obviously dropped to 2 times 10 to the 5th kilowatts per centimeter squared. That was an 84% reduction in power density. I mean, that is huge. Just that small change in the beam size, that small drift in the location of the beam is going to yield a much lower power density, and that is definitely going to affect your process. Okay, so let's talk about how to measure, how this is accomplished, measuring these laser power density. All right, laser power and energy measurement. Number one, you want to pick a sensor. The sensor is going to be defined by your laser power. It's going to be defined by your pulse characteristics. It's going to be defined by your laser wavelength. But measuring CW power, average power, single pulse energy, pulse to pulse energy, pulse frequency, anywhere from picowatts to kilowatts, anywhere from picojoules to tens of joules. You pick your sensor, and then once you've picked your sensor, you will marry that with some kind of meter or PC interface. So you've got a couple examples here. You've got a Starbright meter by Ophir. You've got a Juno PC interface, an EA1 Ethernet interface. Take your sensor, marry it up with some kind of meter or PC interface, and then number three, you perform the analysis. So what you want to see is laser power versus time. You want to see, this graph right here is exactly what you want to see on your laser. You see a nice ramp up of laser power, you see the power stabilize, and then eventually you're going to see the power remain consistent over a longer period of time. That's when you know that you have a nice healthy laser, is when you can achieve that. And then with respect to beam profiling, it's a little bit different approach, but this is, again, your power energy is you're verifying the top part of that power density. Your beam profiling is going to be used for verifying the bottom part of the power density. So there are scanning slit profilers or camera-based profilers. The bottom unit there is called the beam watch. This is what measures that Rayleigh scattering, measures the beam caustic all in real time. We use silicon CCD and CMOS cameras to achieve that, phosphor coated for mid-IR wavelengths, in-gas germanium, broadband pyroelectric, all kinds of imagers. You pick the imager based on the wavelength and the beam size and some other factors. You take that imager, you marry that with your analysis software. On the left here, you see Beam Gauge, which is our beam profiling software that measures the intersection of the beam spot. The beam watch, you see the beam caustic being measured here at one time. So you, as far as the approach with beam profiling, there's an approach that must be followed. Number one, there's an attenuation process that needs to take place. Laser power must be reduced to a suitable level to be imaged by the imager. So once that beam power, if it's necessary, sometimes it's not necessary, but if it's necessary to reduce that laser power, and then you want to size the beam properly. Once it's attenuated down to a certain size, you want it to be either small enough or big enough to analyze on the imager. And then once it's attenuated in size, you want to take that image. You want to send the image to that imager, whatever imager you're using, and then the imager will marry up with the beam analysis software to do the analysis. So that screen right there is just the basic approach of how you get a beam profile. All right, so 3 case studies. We're doing really good on time. 3 case studies where these measurements techniques are applied and how these measurement techniques have helped customers solve some problems. Number one is a laser marking application. So this particular laser system, I apologize, I don't have a picture of it, but it is a it's a laser marking system. It's a fiber laser system. It yields an average power rating of 50 watts. It is a pulsed laser. Usually the marking lasers are pulsed at kilohertz rep rates. The application is marking and scribing for this particular system, and the trouble that we were seeing was inconsistent marks. So we were interested in finding out what was yielding these inconsistent marks. So the measurement equipment that we used to analyze this laser, you see a 150 watt power sensor, which measured the output power, coupled with a Juno PC interface running this StarLab software that you see pictured here. We also took a beam profiler. This is kind of an older application, but it's nonetheless, it's one of our older products, but it was the SP620U CCD, silicon CCD camera, suitable for the 1 micron wavelength. You see the beam attenuation system that's sitting on the front end of the camera that reduces the laser power before it reaches the imager, and then it's running the beam gauge software. So we collected all this data. We looked at the beam, looking at the beam profile first. The beam profile looks, it looks nothing really out of the ordinary. It's a nice balanced energy. It's a little elliptical, so that might affect the laser mark depending on how small the mark is. But overall, the beam profile looked like it was very suitable for this particular application. And then we checked the laser power, and we got this. So we see the laser turn on, it comes up to power, and then it, for whatever reason, it started to drift off. Now this was a fiber laser, so it was really kind of unclear why it was doing this. It was starting to drop off. So if you're thinking about your power density, you've got a nice beam profile, so you can check the bottom of that expression off. But the laser power, because it was fluctuating so much, it was causing these inconsistent marks. So basically, when we're talking about power density, you just really don't know what your power density is going to be doing through the duration of this mark. So say, for instance, you're marking this QR code, and you really do need to have, number one, a consistent beam profile, consistent beam shape. If you have inconsistent beam shapes, you're going to have different sized cells, which could throw off the readability of this QR code. But really, if you're looking at this particular laser that we are measuring, since the power was fluctuating so much, how would that affect the mark of this QR code? How would it affect the overall integrity of this QR code if one or two of these cells were missed? If it didn't mark for whatever reason, it could very easily invalidate this particular code if that happened. All right, so case number 2, let's look at CO2 2D cutting systems. There are a ton of these lasers out in the marketplace, out in manufacturing. These are workhorses. They are very easy to work on. They just, they take a licking, keep on ticking. That there are a lot of laser operators and laser maintenance personnel who know how to run and maintain these lasers. So as a result, they just keep maintaining these lasers, and they keep going. But these typically are 2D source, CO2 source machines. There are a lot of fiber lasers which are kind of replacing this technology, but that's not to say that there are still a lot of these CO2 lasers out there producing parts. The case studies we're going to look at are anywhere from 1,500 to 5 kilowatts. They vary in laser power, but they're typically, with these systems, the beam is generated with a resonator and then sent through free space, hitting a bunch of reflective optics through a bellows, and then finally to the processing, to the cutting head, which sometimes I've seen that a lot of problems with these bellows. They can damage and they can cut. which introduces contamination onto the optics, but that's that's part of the problem of the system. But the application, sheet metal cutting in most cases with these particular cutting lasers. The most consistent problem that we see with these lasers, or that I've seen anyway, is either inconsistent cutting or loss of cuts. And there can be, like we mentioned before, there can be thermal effects on these laser systems as well, which can cause the focus spot to drift off of focus. But usually when there is some kind of thermal effect, usually caused by some kind of contamination of an optic, that's where these lasers can see some problems. As far as the measurement equipment, you see pictured here, this device is called the mode check. This is a beam analysis system that we developed for CO2 lasers. On this particular device, there is a 5,000 watt sensor that's mounted to the bottom of this device to measure up to 5 kilowatts. That sensor is married to a Juno interface running the StarLab software on a local PC. And then this is the mode check beam analyzer. In this case, there was a re-imaging lens. The re-imaging lens was used to measure, so we didn't have to take the focusing lens, or I'm sorry, the head out of the lens in order to analyze the beam. So that's a picture of the system. Again, we're talking about power density. We're talking about the amount of laser light versus what the beam shape is doing. All right. So we took some power measurements, and you can clearly see that there was a ramp up, there was a stabilization, and then power was just fluctuating all over the place until about 45 seconds later or so, it finally came up to the 5 kilowatts that was expected. But if you can picture or if you can imagine what's going on in this cut, you're starting off with a low power, you're fluctuating power, and then you're 45 seconds later, you're eventually getting up to the cut. But if you can imagine what that cut looks like during this time, it was pretty ugly. Moving on to the beam profile. The beam profile, looking at it, this beam profile was expected. There was a donut mode that was expected. Nice and round. There was an ellipticity of about 95%. So nothing really earth-shattering with the beam profile, but you can definitely see from the output of the laser power that this laser was causing some inconsistent cuts. Again, what's power density doing when your power is fluctuating this much? You really just don't have any idea. The second laser cutting system that we measured, this particular laser was exhibiting about a 20% loss of laser power from what was being programmed to what was being measured. So as a result, you just can't say for sure that you are producing good parts when you have a power drop like that. In this case, probably what was happening is there was a consistent drop in laser power, and you see what operators do. They want to keep making parts. They want to keep making good, consistent parts. So what will they do? They'll just continue to ramp up the power until it eventually reaches a point where you just simply can't do that anymore, and you've got some real problems on your hands when you continue to operate the laser like that. Looking at the beam profile, in addition to the laser power drop, you see the laser intensity of the beam was really kind of off center. It's really kind of balanced to the southwest there, where it's supposed to be, round and nice and circular. So the laser power combined with the the insufficient beam profile there was really causing some big problems for this particular laser. Again, you don't know if power is dropping that much and your beam profile is exhibiting something like that. You just really don't know what your power density is doing with respect to the process. And then the third the third CO2 cutting system that I want to take a look at, this particular laser, we took a laser power. The laser power came up to power, fine, and then it started to drop off and it eventually would have, continue to drop off. But in about 30 seconds, we just turned the laser off because we could see that the laser power was just not producing efficient laser power over the duration of the cut. Again, when it does this, you don't have a consistent laser power. You just don't know how that's going to affect your power density. Moving on to the beam profile, you can see that at beam on time, it was producing a nice round beam. It got a little bit more intense, and then it started to just completely fall apart. So 3 to 4 seconds, and then several seconds after the beam was on, it just the beam profile was just not consistent at all. Likely there was a focus shift, some kind of thermal effect on this particular laser system, but it was causing the beam profile to really fall apart. Again, power density, when you're trying to verify that you have a consistent power and a consistent beam profile, you just simply cannot do this with these particular set of settings. So it is really unclear to know for sure how this laser was performing with respect to time. And then the third case study I want to talk about is fiber laser remote welding. And now this particular lab was developing a weld on aluminum with a multi-mode 6 kilowatt CW fiber laser. There was a scan head that was connected to a robot arm. Probably a lot of you are very familiar with that particular system. It was a remote welding system that was doing on-the-fly welding. It had a 500 millimeter working distance and a 300 millimeter spot size. The problem that this particular lab called me in on is that they were having loss of penetration of the weld. So they were turning the laser on, it was starting to penetrate fine, and then over the duration of this 4-second weld, it would lose penetration. The measurement equipment that we use to measure the laser, you see on the floor here, is the 10 kilowatt water-cooled power sensor. This is married up with the Starlight meter that I had to measure laser power. And then as far as the beam profiling goes, there's the beam watch beam analyzer. Laser would come down, move through this aperture. It's not touched by the beam analyzer. 100% of the beam goes down to the laser sensor to collect the laser power. So that's a picture of the setup there. And then here is a picture of the beam analysis software. And just to kind of explain what you're seeing here, you see at the upper left, you see the measurements that were selected to be measured. Right below it is an analysis of the beam caustic, and this is the beam caustic at this plane right here. This is a definable cursor for that particular software or that particular process. In the middle, upper middle here, you see what the beam profile is looking like at this cursor. And so we'll see how this changes in a second. And then this graph right here is a graph of focus shift. So what you'll see in a second here is you'll see the focus shift that is measured and how that affects the beam profile, how it affects the caustic, and how it affects this graph. To the right here is an image of the beam. So the image, the beam is focusing down currently to this point right here. And then if you can picture it diverging again past that point. There are 2 markers here on each side. One is a blue marker. The blue marker is where the laser focus spot starts out at. And then the green marker is a dynamic measurement of the focus shift. So when the beam turns on, it starts here, and then you'll see a dynamic measurement of the focus shift. Again, we're talking about how this affects power density. We have a nice consistent 6 kilowatt measurement, but how is the beam size at the process going to be affecting the power density? And I'll advance to the next slide, and we'll start to play that. You'll see the focus shift start to shift upwards very rapidly, but notice what the beam profile is doing at the work site. It's completely falling apart, and you can see this graph of focus shift over time. So at the end of this measurement, we measured it for several seconds, and it shifted about 25 millimeters for the duration of that particular beam on time. And it started over just now. So You can see the focus shift. Again, pay attention to what's happening with the beam profile and the caustic. And also, this plane, if it represents the work site, what's the beam doing at the work site, at the process? It is very easy to see that, with a consistent laser power, which oftentimes tells a good indicator of how the laser is performing, but it does not show you the entire story of how that laser is performing. So with a consistent laser power, a very inconsistent beam size at the work site, you just cannot really know for sure. You don't really have any confidence in the power density that's being applied to the process. Here is a picture of a remote weld head. This was not the same one, but it's a picture that I got of one in the site, or in a on site somewhere. You can see that there is some contamination on this cover glass. That's usually where these thermal effects come from. This one is really very visible. That particular lab that I was working with on this case study, there was no visible contamination on the cover glass, but they did eventually determine that the cover glass was the main culprit that was causing this focus shift. But in this picture right here, you can really see it very bad. You can see it in when you think about how badly this cover glass is contaminated and how that is absorbing that laser light, you can quickly come to the conclusion that this cover glass needs to be changed to avoid those thermal effects. All right, so just some closing thoughts as we close out this webinar. As advanced and as stable as laser systems are today, they are still susceptible to these physical properties and human error. And I hope that I was able to effectively illustrate that to you today, that just because laser systems are advancing in their technology and they are getting more robust, the processes are more robust, but the bottom line is they are still susceptible to physical properties. And because human beings are maintaining them, are operating, they are still susceptible to human error. These limitations will ultimately translate into a degradation of system efficiency and changes in the system behavior. So understanding, and really the case that I want to make to you today is understanding how these changes affect the way the laser interacts with the process, is really best understood through the frequent measurement and analysis of these key performance indicators that we talked about in this webinar today. So that's all really that I wanted to present to you today. We've got a lot of time left over. We'll open it up for questions now. I'll turn it back, Joanne, I'll turn it back over to you if you want to open it up for questions, and we'll go from there.
Thank you very much. Yes, we do have time to take a few questions now before we close. Everyone, if you have not already, please go ahead and type your questions or comments into the webinar chat. All right, so my first question is, it looks like your BeamWatch product was used to measure the focus shift on a fiber laser. Can it be used on a CO2 laser?
Yes, that is a really good question. That is actually a question I get quite a bit. The BeamWatch product, it only works with, currently only works with the products that are released with near IR lasers. So right around 930 to 1100 nanometers or so, something like that. It's really only designed for those wavelengths. We are coming out, since electronic vehicle components are using more visible wavelengths, we are coming out with a version that is that is engineered to engineered to measure visible wavelengths, specifically green wavelengths. But with the wavelength being 10 times the value at the CO2 wavelength, it's impossible for us. I can't say impossible because I don't know for sure, but it's very impractical, let's say, to measure the laser using the Rayleigh scattering method that the BeamWatch uses. But that's a good question.
Thank you. This next one is, what other laser measurements are important to measure, and how often should they be measured?
Yes, that's a good question also, because this is one I get quite a bit, is how often do you take, I want to measure laser power, how often do I measure laser power? And the bottom line is, with respect to the industrial lasers being used for processing, used for part processing, it really is up to you. There really isn't a right or wrong answer. I've got customers who measure their laser 3 times a day, once a shift. I've got customers who measure their laser just in maintenance, maintenance cycles. So, once a quarter or whenever they maintain their lasers. There really isn't a right or wrong answer. It really just comes down to your weld spec or your cutting spec. As far as the life of the laser, there's another discussion to be had about that altogether. But like laser source manufacturers, they will be really very particular about having a very accurate laser power output measurement. So they're particular about that. It also has to do with the where the laser is being used. So for instance, if it's being used for medical device manufacturing, laser power is a very, very accurate laser power measurement is very important to those lasers, as well as a beam profile, verifying beam profile. So it really depends on where the laser is being used. It depends on what stage of the laser life cycle where the laser is. Is it an infant laser? Is it being integrated into a system? Is it being run off at a factory, or is it in its production stage? There's really very different answers for each stage of the laser life. But when we're talking about production, that it really is, again, it really is up to you when you want to take those measurements.
Perfect, thank you. This next question is, it looks like these are tools that can be used for maintenance. Can they be integrated into a laser cell also?
The answer is sometimes. So some of these products can be integrated into the laser cell, and we have variations of some of these products. For instance, you saw the Beam Watch product that we used to measure the remote welding laser. We have a variation of that product called the Beam Watch Integrated, which is the Beam Watch coupled with a power meter, all sending information to a PLC, and then the PLC can communicate with your robot system. That particular system is designed to be integrated into the cell and left there. If you do take these products and integrate them into a cell, you do want to be mindful that it is producing process debris, and you want to protect the products from this process debris. So that is a consideration. Some of the products just are not suitable to be integrated into a cell. They are just really just used for periodic maintenance measurements. But the answer is yes. Usually, a lot of these products can and really should be integrated into a laser cell. Yep.
Thank you. All right, this next question is, what is the most common purge gas, CDA or N2, or are other gases ever needed? And also, what gas velocity is needed?
Yeah, that's a good question. I'm not that much, of a gas expert per se. The most common that I've seen is either compressed air, clean compressed air, or nitrogen. Those are the two. I've seen also argon being used, but argon is a relatively expensive gas to use. But really, any inert gas can be used. Definitely not oxygen. I'd say nitrogen or clean compressed air. The velocity, I would say that really has to do with the design of the head. I'm not sure I really have a very good answer for you on that. So I can certainly follow up with you after the webinar if need be.
All right, thank you. And I think we have time for one more question. This
Okay.
final one is, what did you mean by caustic measurement?
Caustic measurement, yeah. So the caustic measurements has to do with the beam as it focuses down to a point. and then it starts to diverge again. The information in that beam caustic can tell you a lot of things about the performance of the laser and the quality of the laser beam. So, for instance, the m² measurement, the beam parameter product, the K value, those are all related, but those are all caustic measurements. The Rayleigh length, which is roughly defined as the amount of a laser beam that can be used for a process, and it's that there's a length that Rayleigh length is used, and then the divergence angle. So if the beam is focusing down to a point, how fast is it focusing down to a point? All those characteristics, all those beam characteristics are known as caustic measurements.
All right, perfect. Thank you. Everyone, if we have not answered your question already, please look out for a reply from us later. And if you do think of another question or would like to request a copy of today's slides, you can let us know by emailing webinar@photonics.com. That's WEBINAR@photonics.com. And just one final note, the whole session was recorded. It will be available on the Photonics Media website shortly, and you will also receive a link to that in your email. I'd like to thank John McCauley of MKS Ophir one last time, and thank all of you for participating today. This webinar was presented by MKS Ophir and hosted by Photonics Media. Thank you, everybody.